Hello everyone, my name is Juan Fraire and I'm presenting now our research in managing routing scalability in space delay tolerant networking. This presentation has been given at the STINT workshop, the Space Terrestrial Internetworking workshop, which is held in the IEEE International Conference on Wireless for Space and Extreme Environments, YC, and this was presented in 2018. This work is done in cooperation with the National University of Córdoba, CONICET, the Argentine Space Agency, and Scott Burley from the Jet Propulsion Laboratory at NASA. So I'm not saying anything new by saying that space networks continue to grow both in size and in amount and quantity of networks. We are now talking about mega constellations. There is like a renewed interest in providing services via hundreds or even thousands of satellites. And we are reading the news every day about SpaceX, Starlink constellation, which are talking of around 7,000 satellites, if not more, in total, in a constellation in a LEO orbit, in a very low LEO orbit as well. Different missions are basically being launched every day, and two main challenges are arising and will definitely arise and will become a problem in the very short term in this type of network, and are these 2 points I'm highlighting here. One of them is integrating these networks with ground networks, which are of very different nature, and also integrating these networks between themselves. We will have so many networks orbiting the Earth, and integrating themselves can be a great opportunity to repeat in space what Internet has done in Earth in the 90s. And the second point, besides integrating, is the scaling these networks, achieving good performances in networks which has hundreds of nodes or even more than that. So this is the challenges that we are highlighting in this presentation. So challenges of integrating this network. These networks will be integrated with ground networks and with networks in geostationary orbits, and beyond that, potentially in the interplanetary network in the future. So 3 particular families of networks can be observed in these ecosystems we are describing. One of them are challenged networks, where challenged networks are networks which are rather dominated by delay, very high delay, such as in interplanetary networks, or link disruptions, such as seen in challenged constellation of small sats, where links are unstable, are sporadically enabled because of energy constraints, and so on. These challenged networks are only one part of the ecosystem that we are describing. Dynamic networks are another type of family that we will see here. I'm referring to satellite clusters and constellations that are, for instance, flying in a flight formation, and that they can sustain a continuous connectivity between all the satellites in the network. These are typically, for instance, we're talking about Iridium or this type of systems. And also I'm talking about mobile networks with mobile devices that connects with an infrastructure such as 4G and 5G. And I'm also talking about ad hoc networks such as MAN-A and MAN-8, which are networks that connect without infrastructure, and they're able to utilize device-to-device communications. These are dynamic networks in the sense that the topology of this network is continuously moving, but in contrast with challenged network, we're talking about networks that are continuously connected in an end-to-end path. So every node is able to reach all other nodes. There is no partition in this type of networks. And then we have the traditional static subnetwork, which are networks that can basically guarantee a continuous topology. And this is obviously one of these is Internet, which is a cabled infrastructure, and therefore is a continuous, connected and very stable topology. And potentially geostationary networks, which are networks where a single point in sky is continuously seen, and therefore the connection with this point and potentially a constellation of video satellites can also be considered a static subnetwork. So the challenge here is that each of these family of subnetworks are already routing data with specific algorithms and strategies that are very well suited for this type of family. So aiming at having a homogeneous routing scheme is not convenient for a complete ecosystem embracing all these subnetworks. It will be mandatory to leverage heterogeneous routing schemes. So in static subnetworks, we are already talking about OSPF or static routing. This should remain like this. There is no gain in modifying this type of strategy. Dynamic subnetworks such as MAN8 and BAN8, they're also using their own routing protocols, and same for challenged subnetworks with disruptions and delay on the links. This is the challenge that this type of system will need to face: how to route data on an with an heterogeneous approach. The second challenge is to scale. Topologies in networks, in particularly those that are dynamics and those that are grows in time, particularly challenged networks, these networks topologies complexity growth with nodes, and this happens for all networks. Obviously, they grow with links between these nodes, and they grow with the schedule horizon in the case of dynamic networks and challenged networks, where the time dynamic of nature of the systems basically imposes to use data structures that can model all this dynamic of the network in the future. And this is the case of contact plans that in space network that are fed to the routing algorithm that is used to eventually derive which is the best net hub and to forward the data as the data flow in the system. The problem of scalability is that current routing solutions, particularly for challenged networks such as contact graph routing, which they're not scaling they're not conveniently scaling. This is a study performed by the Ruhai Wang team about the complexity of contact graph routing, which is the state-of-the-art routing for challenged networks, and scalability both in terms of number of nodes and number of contacts, which is basically schedule horizon, can be seen on the schedule horizon. It grows with practically, in some cases, in an exponential fashion. So the way that we are proposing to tackling both challenges, the integration part and the scalability part, is the regionalized routing. So this region-based approach basically has two features. One of them, we will honor region-specific routing solutions. We will leave each region to use its own routing solution, which fits the best for this type of network. And on the second hand, we are going to be able to localize the routing computation effort even in sub-networks which are of the same family. So the region hierarchy here basically will render two different types of routing. We're going to be talking about intra-region routing, or intra-RR basically, which are valid only within a given region. So let's say within internet we will still be using OSPF, and within let's say MAN8 we're going to be using AODB and so on, and this will stay as it is. But there will be an inter-region routing, which will be a routing will be valid between regions. This is the key factor here. This is the thing that is gluing all the regions together. There will be designated passageway nodes that basically connect region between themselves and each other. And there will be, so therefore the region selection criteria is going to be driven by the network type or the network family that we saw, whether challenged, dynamic or static, and also will be driven by the partition of this of a given family of network in order to achieve scalability. So the inter-region routing requirements, which is the gluing factor here, will have three main requirements to cope with. One of them is that these regions will need to tolerate delay and disruption between them. This means that we will have regions that will be temporarily isolated from each other. This is particularly true in the case of space networks and deep space networks. We will have directional links between regions also, and this means that probably bidirectional links are not going to be always available between regions, and this is also particularly true from space, where there are some spacecraft or cases, many actually of them, where transponders, or where we have transmitters at a given band which has no feedback or return channel. So this is something that will need to be met by inter-region routing. And also the connectivity information between regions will be generally known, and this is particularly true because of the orbital propagator that allows to estimate where satellites are going to be in the future, and therefore we are going to be able to derive how these regions connect to each other, and therefore use this information in our advantage. So the real thing is that there is not an existing inter-routing, region routing framework meeting these specs. There has been some previous work we have surveyed in the paper, but none of them actually cope with these three specifications we are discussing in this slide. So the model is as follows. This is basically the same network we have seen in the first slide, and the idea is to create different regions with the different families of network that we're going to use here. So in this case, we have region from A to F, and we have here highlighted as red what are going to be called passageway nodes. These are nodes that are registered, or let's say they belong to two regions or more at the same time. This means that the nodes are going to be able to talk as many routing protocols as many routing protocol instances as regions they are registered to. So for instance, in this picture, we can, if we take a look at node 60, we're talking about a gateway on ground that is going to be able to talk the routing protocol that is being used in the geostationary relay network, and it's also going to be able to talk the protocol of internet routing. Let's say that we're talking about OSPF, for instance. And this is something we can highlight about passageways node is, as we can see here in this figure, is that some of them can receive data. They are RX, or they are the squared icon. Some of them can transmit data, such as the triangle one, and some of them can do both. So here is how we are actually respecting this condition that nodes in the region can have directional or unidirectional links between the different regions. So as a general statement, nodes in this intra-region solution will need to have a unique identifier. This will be dependent on the network infrastructure. If you're using the large area networking protocols such as boundary protocol, then this will be an endpoint ID identifier. If by some reason you are using other identifiers such as IP, then this should be IP. We mentioned that some nodes may receive, transmit, or both. There will be an object called a region database that will have to be distributed or learned by the regions in such a way that the passageways nodes can learn where are the regions, to which region a given node is registered at a given moment, in order to calculate an intra-region path to be forwarded. And also nodes within a region will need to know if a given destination is hosted in the same region, local region, or is hosted in a remote region. Nodes may update the registration from region. They can register to a new region, they can remove the registration from another region. So this should be dynamic and this should be tolerated, although the frequency of such updates should be is assumed to be quite infrequent in comparison with the operation of the network. So we also say that if a given node can receive packets of a region A and can transmit in B, we said that this node is a passageway and that we have a bend in node E transmitting from region A to region B. As we said, nodes with one or more bends are called passageway nodes. So the rationale of this approach is that within a region, nodes can optimally route data using the regional topological information. This means that local nodes will be able to talk frequently with neighbors using the optimal and the full available information of the local routing protocol that's being used in that region. When talking within region, the routing decision could be suboptimal because we will not have the topological knowledge of neighboring regions. This is because basically we are hiding routing strategies and information within a region, which basically is the feature that allows integration and scalability. However, this hiding fact comes at the expense of a decrease in performance, and this is what we aim at studying in this presentation. So we are proposing an inter-region routing procedure. This is just one possible of this. There might be another ones. So this is one possibility of inter-RR procedure, and it is as follows. In this case, we're seeing at the same region map example of the previous slides, and the idea is to build a static graph of all the possible region path that we have. So let's say in this example that we have a source node in the region A that wants to reach a node which is in region F. So I will note this node in region A will not have the topological details of region B, D, C, and E, nor F. However, this node will be able to detect which is the local passageway node. In this case, is node 10. And this node 10 is going to be able to create this static graph of all the regions that are available in the system. And these regions basically will allow us to create a graph where the node in the graph or the vertices are links between the different regions, directive links. And each one of these links will be matching one passageway node, and these links will eventually connect to other links, and we can build a graph in such a way that we get to a final destination of the region, in this case region F, and then region F will be able to deliver this packet to the final destination, because node 60 in this case, which is the passageway node of F, also pertaining to region E, will have the local information of region F in order to forward this data using the local routing procedure. So this is the detailed algorithm on how to build this graph and how to use it. You will find it in the paper for more detail. So we're going to evaluate this approach, and the way we use to evaluate this is to have three different approaches. One of them is the global full knowledge, GFK. And with GFK, we say that we have a single contact plan. We have a single region. So this is the case of the figure in the upper part of the slide here, that we have all a single topology that is distributed to all nodes and is used as the unique topological knowledge. I didn't mention that for this evaluation we're going to use CGR for all cases, contact graph routing, the DTN routing algorithm. The second approach we will be validating is the local regionalized knowledge. This is the proposal we're actually describing here. So we have one contact plan per region. So we can we are dividing this topology in two regions, the red one and the blue one. And we have an intermediate node here that actually belongs to the two regions at the same time, and this would be the passageway node. that actually drives data back and forth between the two regions, right? So this will be this is a event we're actually having here in this topology. And then we have the global regionalized knowledge, in where the decisions that we took of using this node here, n as a passageway node, remains as is, and the other contacts that were removed from the topology are also removed from this unique contact plan that is going to be delivered to the complete topology. And what with the scenario we will use to validate this idea is a realistic satellite scenario composed of 3 different LEO satellite constellations, as highlighted here in this picture. These are like a long track constellation of satellites, where these satellites can sporadically visit each other and so on. And then we also have region A, which is a network in the ground in the South Pole. And then we have a region F with another ground station in the US in this case. And then we have a region E with 3 geostationary satellites. And here we have a table with the parameters we are assuming for this network. And we will split this network in regions. We're talking about a scenario with a single region. We will be talking a scenario with 4 regions, basically describing all the LEO constellations in this case, also the ground and the geo. And then we also split in total in 6 regions, which are the 6 regions that are highlighted here in this figure. We will validate this idea using DTNs in an open source scheduled DTN simulator based on omnets. And these are the results. So on the left hand side of the slide, we see the routing computation efforts. This is basically what allows scalability. So on black, we see that we are talking about the single region, or the traditional way of doing this. We could be like the full topological knowledge to all nodes. We can see that the routing computation effort is the highest in terms of seconds. The details of the platform of the simulation are detailed in the paper. And also you can see the mean delay per bundle on the right hand side. This is the best performance, as the bundles are delivered with the lowest possible delay. This is the black curve we see on the right hand side. When we talk about 4 regions, we have the global approach one and the local approach. The global approach is better in terms of the global approach. I mean, is more expensive in terms of computation effort, because we have a global knowledge, but filtered with the decision of the band that we're actually using. And the local regionalized knowledge is better in terms of computation effort, because only local nodes take decisions on the routing, only on the local region and not on the global one. And this actually pay off in terms of routing computation effort, but does not pay off in terms of mean delay per bundle. And the best performance approach in terms of computation effort are the 6 region approaches, particularly the localized one. But obviously these are also the worst performance in terms of mean delivery per delay per bundle. So we actually have here a clear trade-off between routing computation effort and the mean delivery delay per bundle, which is actually what enables scalability in this type of systems. So we have introduced this region-based approach to integrate and scale space networks. We have measured and seen in a realistic scenario how this trade-off is evidenced in the data delivery matrix and the computation effort that nodes need to do in order to route data in these systems. This is the first step of a long way in improving this regionalized approach. Discussions are still held regarding unified nodes identifier. This will depend on the architecture that will be used. Many of us are DTN prone, and we will tend to choose endpoint ID as an identifier, but other options could also be considered, such as an IP, if we are talking in a full IP network. And many challenges remain, particularly in how do we define this region? We have, in the scenario we have described, we have been very general, and we have not discussed how have selected the region, but there might be other options with different trade-off in terms of data delivery and performance. So actually defining this region and defining the region traversing cost, which are the passageways, which are the bands, has definitely an impact in this trade-off, and they must be evaluated, and a specific region design scheme should be considered to correctly operate and design these networks. Same happens with the dynamic regions and the automatic learning of region database. Do we need this region database to be configured and provisioned in advance, or there is a way for these nodes to learn these regions and use a hierarchy of the regions and so on in order to learn this dynamically? This is also an open research path for in this context. So this is all of the presentation on scalability and integration of future space networks. And well, I'm open for questions, and thank you very much.